We have seen many techniques to reconstruct geometry from image inputs, but most of these reconstructions only considered a particular object or even just produced a single depth map. And often when we want to do reconstruction, we want to reconstruct entire scenes. We want to reconstruct larger scenes, scenes that are composed of multiple objects. And then the question becomes relevant how to combine these individual reconstructions into one big consistent 3D reconstruction of the entire scene. And one technique that is very popular in this area and is used a lot also due to its simplicity is called volumetric fusion. And that's what we're going to look at now. Here's an overview of a traditional 3D reconstruction pipeline. The input is a set of images. We first estimate the camera poses, and we have seen techniques for doing so, like structure for motion, bundle adjustment. From these estimated camera poses, we can then, and the images, we can then compute dense correspondences using binocular or multi-view stereo techniques, or monocular or active, or shape from shading techniques, or techniques that combine all of these aspects. And one intermediate representation that might be the outcome of such a calculation might be a depth map for each of the reference images that we have. And now depth map fusion is about taking all of these depth maps and combining them into one consistent 3D reconstruction as shown here on the left. So let's look at how this works. And in order to understand how it works, we first have to understand the representation that it uses, which is not an explicit representation, but rather an implicit representation of the shape. Here we see a mesh-based representation. This is a shape, in this case is a circle, that is discretized into a set of vertices and edges. You can see the different vertices here enumerated, and the set of edges, which indicates that there is an edge from 1 to 2, 2 to 3, 3 to 4. And if we would do this in 3D, this would of course be a set of vertices and a set of faces. But here for simplicity, we illustrate everything in 2D. So this is an explicit representation that stores the geometry in terms of vertices and faces. But it's not an ideal representation. While it has been used for fusion, it's not an ideal representation for fusion. And it's very hard to change topology with that representation. What we're going to do instead is we're going to look at an implicit representation. The simplest implicit representation is a simple parametric form. For example, we can represent a circle as a level set of this parabola here. We have a function f of xy, which is x squared plus y squared minus r squared. And of course, if we set that equal to 0, we arrive at an equation for a circle. So we have implicitly defined the surface, the shape, as the level set of such a function. Now, in the next lecture, we're going to actually talk about such implicit models more in the context of representing these functions using neural networks. But this is a rather recent line of work. And so we're first going to focus on what has been done in the past, in the last 20 years, which is a discretization of this implicit space. And in particular, we're going to look at so-called sign distance functions that measure distances from the center of each of these voxels that we're looking at here, or pixels in this 2D example, to the actual surface, the closest distance. So we are discretizing the space as such, using a resolution as it suits us, depending on the memory and compute that we have available to us. And then we insert at each of these voxels or pixels, we insert a value. We set the value of that pixel or voxel to as the distance to the closest surface. So in this case, the value of this voxel here might be 2.5 because it's 2.5 units. The center is 2.5 units away from the closest surface point. Or here we might have -3 because it's 3 units away. And we have a -3 here because it's a sign distance. So we indicate with a positive sign that this voxel is inside the object, and with a negative sign that the voxel is outside the object. For example, here we have a voxel that's outside the object, but it's closer to the object than this one here. So we set the value as -0.6, which is roughly this distance here. In some formulations, you will see the signs flipped. That is arbitrary. That's up to definition. We can, of course, also define the inside to be the negative distances and the outside to be the positive distances. But it's important that we define a sign distance so we know what is inside and what is outside. So this is the discrete sign distance function representation that stores a sign distance to the closest surface at each and every voxel in this representation. And the surface is hence also represented, similar to the continuous case, as the level set of this discretized representation, where we have to interpolate now in order to actually find the surface, as we will see. A crucial advantage of implicit models is that they allow for representing arbitrary topology. They allow for representing topology changes. For example, in this case here, if you look at this scene and you take this slice, this red slice through that scene, and that slice in XY coordinates is represented here, you can see that there is some pixels in that slice where the function value, the SDF value, is smaller than some threshold or smaller than 0, and there is some areas where it's larger than 0. And these by just changing the corresponding voxels, you can change topology. You can switch this object off. You can remove this object by just turning all these values to be positive. So it will merge into the background. You can create a new object here by taking these positive values and turning them negative, and an object will appear. So the topology, the number of connections between surfaces, so to say, is changing depending on the implicit representation. It can be changed in an easy manner. It's much harder to change a mesh because you have to connect vertices differently if you change topology. But here you just have to change the value of the SDF value of the voxels. And here's an example with different topologies. So here we have a topology with holes. Here we have a simpler topology. And I want to show you a video. This is a newer work that we did, but it nicely illustrates how such implicit models allow for changing topologies. You can see here now we have genus 0 changing to genus 1, 2, 3, 4, adding more and more holes over the time of the optimization of this implicit representation. And it's no problem at all for this representation to do this, to change the topology, to add holes, to add object, to remove objects, etc. Okay, so given this representation, what do we do? Volumetric fusion typically has 3 steps, at least if we assume depth maps as input. The first step is to convert the depth map to this discrete sign distance field, sign distance function representation that we've just seen. The second step is to actually perform the volumetric fusion, and the third step is to extract a mesh from the fused sign distance field from this implicit model. So we convert an explicit representation to an implicit one, we do the fusion in the implicit space, and then we convert it back to an explicit representation. Let's start with the first part, depth to SDF conversion. Unfortunately, the problem is not as easy as I've illustrated it before, because the true distance to the surface is often unknown. What we often only know is the depth of the surface at for a particular ray, along a particular ray. So for example, for this surface here, we know that the surface intersects that ray here, but we don't know what is the closest point on the surface. And therefore, what SDF fusion methods often do is they assume, and depending on the complexity of the geometry, this is a better or worse assumption, they assume that this distance to the surface can be approximated with the distance along the ray. So here we have the distance along the ray. This is not the distance to the surface, right? The distance to the surface here might be 0.5, but the distance is slightly larger because we're measuring distance to the intersection along the ray from the voxel center. So for each voxel center, we measure now distances along the ray, and we consider the voxels that intersect the particular ray. So for this ray, we consider all these voxels that intersect. We take the voxel center and measure distances to the intersection along the ray, because that's something that we have easy access to. And it's a good approximation, for example, in the vicinity of the surface. If you would consider, for instance, this voxel here, and there would be another object here, then of course the distance to this object would be much smaller than the distance to this object. But because we often only fuse, we assume that the reconstruction is pretty good already, and we fuse in the vicinity of the surface. We don't consider distance values that are far away, but just do the actual computation close to the surface. Yeah, so these are the two distances for these two voxels, and we just enter them here as a signed distance. So we have, for example, a negative sign to indicate that we have a voxel that's in front of the surface, and a positive sign to indicate that the voxel is behind the surface. And then this voxel here is further away from the intersection than this voxel, but it's a little bit closer than this voxel, etc. So we can now, for a particular viewpoint, considering all the rays of that particular view, fill this discrete signed distance field representation. We have many rays, 3 of them are only illustrated here, but of course we have 1 ray per pixel, so it's very densely capturing the space, and in between we can interpolate if there is no ray intersecting with a voxel. In fact, in an implementation we would implement it reversely. We would basically take all the voxels and project them into the image and look where, at which pixel they would fall, and measure and take the depth value of that depth map at that pixel. But just for illustration here, we walk along rays. So we have this for the red camera, we have this for the blue camera, and we get these 2 discretized SDF representations, one for the red camera, one for the blue camera. This was about depth to SDF conversion. Now let's see how we do the actual volumetric fusion. And to illustrate this in a more simple example, we look at the orthographic case, where the cameras are orthographic, look in the same direction, so all the rays are parallel to each other. But really, this is just for simplicity of illustration here. This algorithm works also for perspective cameras that are not oriented in the same way. So what we do here effectively, after this conversion into this discretized SDF representation, is to calculate the average of the discrete SDF fields, because this gives us an average of the implicit surface. So by doing the average on this SDF values, we will also average the implicit surface that we afterwards extract. So let's look at an example. So for example, we consider like this ray here, and this ray, and this ray. You can already see that here we have both a blue and a red ray. Here we just have a red ray because the blue camera doesn't see that part of the scene. And these are actually, the blue and the red are actually the surfaces that have been observed by the red and blue camera. So for example, here, if we fill in now, I've just partially filled it in to not make it too complex. But if we fill in the red SDF map, then we have 0.4 here because the surface is slightly behind this boundary. So this distance from the center to the voxel might be 0.4, and conversely might be 0.6 here along this ray. And these values are negative and these are positive, and they are red because they belong to the red camera. Similarly here we have blue values behind the surface and in front of the surface, and for example this value here is 0.1 because this intersection of that ray with that surface is just slightly in front of the voxel center. And now here we have both a blue and a red ray, so we have information for both, and you can see that for instance here the red, well, both the red and the blue values are positive. Here we have negative red values and positive blue values because we are between these two surfaces. And here we have negative values for both. And as already mentioned, what volumetric fusion does is simply to average these values. So we're going to replace these, well, these values here are just occurring once because we just have two cameras here. Of course, in practice we have more and there will be more overlap, but here we don't have more observations, so the average will be the same value. But here we take the average, for example, of 1.6 and 3.4, which is 2.5. So we have, instead of these values here, we have minus 2.5, minus 1.5, minus 0.5, 0.5, 1.5, 2.5. And we do the same averaging in the entire region of overlap. Actually, we do the averaging in the entire space, in the entire domain, but it just doesn't change anything if there's just a single observation. And what you can see now is that, well, the surface intersection, the zero level set, the surface is actually intersecting this ray here, here. No longer here or here, but in the middle. So we have effectively also averaged the implicit surface. If we would now extract the implicit surface from the, if we would extract the surface explicitly from this implicit representation. Yeah, so this is what the surface might look like. You can see there's this, well, this continuity here. Actually, it's not a continuous surface because we have a discrete representation, but you can imagine this to be much finer, and so it might look much closer to this. But we have this discontinuity here because there is no averaging happening here because it's just seen by one camera, and then this part is seen by both cameras, and then this is the part that's seen only by the blue camera. But the surface that we have in the end is a smooth surface that is, or this is a more smooth surface that is an average between this blue and the red surface. How do we do this mathematically? Well, it's simply a weighted average. So the fused distance is the sum over I of the weight I at voxel x, so this is a voxel, times the distance, the signed distance at that voxel x, divided over the sum of all the weights at voxel x, where I ranges over all the cameras, so all the images. And this expression here at the bottom is simply the fused weight, is the sum of all the weights. Yeah, this is actually the sum of the weights, and this is the fused distance. So we normalize by the sum of the weights. And we distinguish the fused distance and the individual distance with the fused distances, calling them, or using an uppercase symbol, and the individual distances of individual cameras, individual measurements, as lowercase symbol. A nice property of the simple weighted averaging here is that this can be conveniently expressed with an incremental update rule, which we'll do as an exercise. And the advantage of this incremental update rule is now, given a particular representation, we can just add an image at a time using constant computational overhead. So we are not increasing computation a lot, we can just add range images at a time and fuse them into an existing reconstruction. You can see here in this expression that di plus 1 just depends on expressions from the previous image or time step plus the current measurements. So it's a very simple incremental update rule, and it supports reconstruction with thousands and tens of thousands of depth maps that are fused into one reconstruction. Now, what about these weights? We said it's a weighted average. Why do we need weights? Well, there's two reasons why we want to have weights. Here on the left, we can see the signed distance and also two different weight profiles. And here on the right, we can see the fused results. The reason why we have these weights that are non-constant is that on one hand, behind the surface, let's say we have the surface here, behind the surface, we want the weights to decay. And the reason for this is that all the values that are behind the surface are just speculation. Everything that's in front of the surface, we know it must be empty space because we have measured the depth at the surface point. So we know that everything in front is empty space. The weight can be high. We are sure that these distance values are correct. But behind the surface, we are not sure. Still, we need to have for some distance behind the surface, we have to have a positive weight. Otherwise, we wouldn't keep a zero level set in our fused result. So we need to propagate information. We need to propagate that we have a positive values behind the surface for a certain distance. But then if we have very thin, it's kind of a trade-off. If we have very thin structures like a thin wall, we don't want to propagate this too much, because if then the camera comes and looks at the object from the other side, it might see that actually the voxels that we have indicated as being inside the object are actually not inside. It's just a very thin structure. So this is a trade-off that we have to play here. The other reason why we want to have a weight profile is that we also want to have the opportunity to downweight less certain rays. For example, if an observation has been made from a very large distance and maybe the measurement noise increases with the distance, as in the case of stereo, it even increases quadratically, or from a very slanted angle, or at the boundary of an object where we are not expecting the measurement to be very precise, if we have that information, we can integrate that by just changing the weight, the entire weight globally for that particular observation. So here we would have, for instance, W2 would be a more confident measurement than W1, which receives overall smaller weight. So it's good to have these weights in the formula. But why is this averaging in general, or this weighted averaging in general, a good idea? This is the formula from before. Well, it is a good idea because it's the solution to a simple weighted least squares problem. What we do here effectively is we're trying to find a surface D, and this is just a long array. It also holds true if we consider a more general setup, but this is just a long array. If we have multiple measurements of depth or distance along array, di, and these are weighted by wi, and we want to minimize we want to find the capital D that's closest to these di's on average, weighted by this wi, which is what we want to do. We want to weigh each of these measurements relative to the weight that we give it. And we want to find a D that averages this out. Then the solution to this weighted least squares problem is exactly this equation here. In other words, D is the optimal distance in the least squares sense. Yeah, this holds at every location X. I didn't include the location, the dependency on X here for simplicity, but of course this holds in general. Now, we've seen volumetric fusion is nothing than weighted averaging in this signed distance, in this discretized signed distance volume. How can we now, from the result, which is also a discretized signed distance volume, extract a mesh? And the answer to this is the so-called famous marching cubes algorithm that's used everywhere in computer vision and computer graphics. It has been developed by Corliss and Levoy in 1996. And the idea is to simply take the discretized representation and try to come up with a triangular mesh that best approximates the zero level set. And the way this is done is by marching. This is where the name comes from. Marching through all the grid cells can actually be done independently for all the grid cells, and insert triangle faces whenever a sign change is detected. And there's two steps. The first step is to estimate the topology, and the second step is to predict the vertex location. So in this is a 2D case here, and here we have a 3D case. In this 2D case, what does topology mean? Topology means where the triangle face is inserted. It could, for instance, be that all of these nodes here are red. All of them would be in front of the surface or behind the surface. Then there would be no triangular face. In this case, there's two are behind and two are in front. And so this triangular surface, this triangular face just intersects both. But it could be that it intersects here, or it intersects here, or intersects here. And these are different, what we call topologies. And in 2D, well, there's 4 of these voxel centers here that we, these dots here correspond, this is actually the dual grid. This corresponds to the voxel centers from the volumetric fusion grid before, at which we have estimated the distance values, design distance values. And if we have 4, then we would have 2 to the power of 4 possible topologies in 2D. But in 3D space, we have 8 because we have a cube. And so we have 256 possible topologies. This is the first step, figuring out the topology just by looking at which of these vertices are actually larger and which are smaller than 0. And this directly maps one-to-one to a particular topology. Now we know where the triangle face should be located. But we don't know exactly where the vertices are. So where should we locate the vertices? Well, if we have signed distance values, then a reasonable thing to assume is that these vertices are at the 0 crossing of a linear interpolation between these two. So if we take a line and pass it through these two values, minus 0.5 and plus 0.5, where that line intersects 0, this is the best possible vertex for the triangle face, because this is the 0 level set. Right, so if we do this, if we set this to 0, then we end up with this very simple equation here. And if we have 0.5 and minus 0.5, then we have 0.5 over 1, which is 0.5. So it's intuitive that the intersection should be exactly in the middle. In contrast, here on the right, we have 0.8 and minus 0.2. So this intersection is closer to here than to here, and so on. And so we get, also in the 3D case, first the topology, and then from the actual values, the vertex location. And we do this for all cells in our grid, and this gives us our mesh. Here's an example of the different topologies that we can observe in the 3D case. In fact, there's 256 different topologies, but they can be grouped into 15 equivalence classes due to rotational symmetry, and these are shown here. Let's now look at some applications of SDF fusion, of volumetric fusion. Maybe the most popular one is called KinectFusion. It has been published by Newcombe et al. At ISMAR, a conference for vision and augmented reality in 2011. And here is the overall system workflow. It's a real-time pose estimation and volumetric fusion method, which uses the Kinect sensor that we've seen before, in particular the depth maps that are obtained from that sensor as input. And it's doing real-time pose estimation using a version of the iterative closest point algorithm, and then updates the reconstruction using the SDF fusion techniques that we have seen in the previous slides. And so what you can see is that if you track now frame by frame, you get a more and more complete reconstruction. So here, after having tracked a partial loop and reconstructed that, we get this reconstruction. And then if we have the full loop, we get an even better reconstruction. And here's a video of how this works. You can see a person that's moving this Kinect sensor in the scene. You can see how in real time, and that's really impressive, I think, at the time, 2011 in particular, reconstructing at a quite high fidelity many of the surface areas in the scene quite robustly. Of course, in this case, the person had to be static because the system assumed a static scene, so had to stand still. An extension of this work has been presented by the same authors in CVPR 2015 that addressed exactly that problem, that the scene is often not static. And that's called DynamicFusion, where from the first frame, a canonical representation has been extracted, and then with every live frame, we can map between this canonical representation and a live frame. So for instance, if we take the canonical representation and map it to the live frame, then these rays would actually bend if we map from the live frame to canonical frame. And now this approach is basically reconstructing non-rigid scenes, or able to reconstruct non-rigid scenes by warping the estimated geometry using a warp field that's also estimated on the fly into the live frame to update the representation after warping and to obtain a rigid and consistent representation. And you can see here the person is moving, is talking, is moving the head. The camera is moving at the same time, yet the reconstruction that is obtained is quite stable. Now this method works only for motions of a certain extent. There have been a few follow-up works that extend this method to larger motions than what is shown here, but this paper has created a lot of buzz in the community and also won an award. You can see the reconstruction in the reference canonical representation. And this is another scene. Here's one work that we did in our group. One problem with volumetric fusion is that it assumes quite noise-free input, which is often not guaranteed depending on the type of sensor. And so it's beneficial to also integrate deep learning into the estimation process, and that's what KinectFusion tries to do. It's basically a 3D convolutional network that uses efficient data adaptive data structures in order to take as an input features from the fusion process and outputs a denoised and completed reconstruction. So you can see here example of volumetric fusion when noise is applied to the input. There's observation noise, and this is a simple variational fusion technique that doesn't do learning. And here at the bottom left, you can see what happens if you train such a learning-based model now on a large data set of 3D shapes that nowadays is often available. And as you can see, it can eliminate a lot of the noise while still keeping details intact. In contrast here in the fusion technique, you can see that a lot of the, due to the strong smoothness constraints that are required, a lot of the details are gone. And another line of work is works that try to tackle the learning problem end to end. What we've seen so far is that at least the learning-based approaches that, let's say, take a set of images and learn an implicit representation in a discretized voxel space, or also a point set representation, had to have a separate meshing step, for example, Poisson surface reconstruction, or run margin cubes in order to arrive at an explicit surface. So the supervision happens at the implicit representation. So we need to have a loss function defined on the implicit representation to backpropagate gradients to the parameters of, for example, the KinectFusion network. And so in this work, this margin cubes algorithm that we have just seen has been, a variant of this algorithm has been developed that is differentiable. It's actually easy to see that the original variant or the original version of the margin cubes algorithm is non-differentiable because of the topology changes. But here, this is a version here that is differentiable, and that combines this topology with the vertex location in a probabilistic manner in order to be able to then backpropagate gradients end to end through the entire system to the parameters of the network, and allows for training using not this auxiliary loss function on this implicit representation that has first to be obtained, but can be directly trained using, for example, point clouds as supervision. That's all for today. Thanks a lot for watching.